Hello all. In this video, we will look at Fenchel duality, which is very useful when conjugate functions can be readily derived. It was developed by Werner Fenchel, who was a pioneer in convexity theory. He was a German-born Jew, so had to leave Germany around 1933 and lived most of his life in Denmark. Recall that the conjugate of a function f is given by f star of y equal to max over x, inner product of x comma y minus f of x. Suppose x and y are two arbitrary points, then by the definition of the maximization operation, we have the inequality f star of y greater than equal to inner product of x comma y minus f of x for all x, or equivalently f of x plus f star of y greater than equal to inner product of x comma y. This is called the Fenchel inequality. The Fenchel inequality is quite interesting and can be used to show some other results as well. One implication is that f of x is greater than equal to inner product of x comma y minus f star of y. We will use this inequality shortly. Next, let us take a look at the biconjugate of a function, which is the conjugate of f star and is given by f star star of x equal to max over y, x comma y minus f star of y. Note that f star is pointwise maximum of affine functions, so is always convex. Likewise, f star star of x is also always convex. So what is the relationship between fx and its biconjugate f star star of x? To get this relationship, let us again go back to the Fenchel inequality. Recalling the inequality we saw in the previous page, fx is greater than equal to x comma y minus f star of y, which holds for all y, while observe that the left hand side does not depend on y. So we can tighten this inequality by maximizing the right hand side with respect to y so as to obtain f of x greater than equal to max over y inner product of x comma y minus f star of y. Now if you just look at the definition of the biconjugate, you can see that the right hand side is exactly equal to the biconjugate of f at x. In other words, f star star of x is a convex underestimate of f of x. If you recall, we were able to derive the weak duality result just from the definition of the Lagrangian dual. In the same way, we have been able to obtain the bound fx greater than equal to f star star of x just from the definition of the conjugate function. So this is the counterpart of weak duality. Next, we have the Fenchel Moreau theorem or the biconjugation theorem, which says that for any proper closed convex function f whose relative interior is non-empty, it holds that f star star is equal to f. This is in fact similar to strong duality theorem, where the condition of non-empty relative interior is reminiscent of the Slater's condition. Further, the usual exceptions that allow us to exclude the polyhedral components or affine equalities, inequalities also apply. In fact, a specific choice of f here can be used to derive the strong duality result that we saw earlier, so that the Fenchel Moreau theorem is more general. Note further that in previous videos we always assumed that the dual variables are real valued because the constraint functions are extended real valued. The Fenchel Moreau theorem does not have any such restriction and is written for x in arbitrary vector spaces. It can therefore be used to derive duality results that are not covered by strong duality theorem. The Fenchel Moreau theorem also allows us to develop a different flavor of duality known as the Fenchel duality theorem. Different from Lagrange duality, the Fenchel duality is written in form of conjugate functions entirely and does not have the concept of Lagrangians. Let us consider the problem min over x f of x plus g of x, where f and g are two functions. X is in the vector space V and it holds that the relative interior of the domain of f intersection with the relative interior of domain of g is non-empty. Then the Fenchel duality result says that the minimum of f plus g is equal to max over y minus f star of y minus g star of minus y. The Fenchel duality theorem follows from Fenchel Moreau theorem and for general vector spaces. Interestingly, we can also establish this using Lagrange duality, specifically using the strong duality result we have already seen. To see the link between the two, consider the problem on the left minimization of fx plus gx, which can be written in the constraint form as minimization of fx plus gz subject to constraint z equal to x. Note that if x is in V, this kind of constraint is not an extended real valued one, but takes values that are also in the elements of V. So for this case, we have to use a more general definition of the Lagrangian that works for any vector space. Let us associate a dual variable y in V star with the constraint so that the Lagrangian is given by L of x, z, y equal to f of x plus g of z plus inner product of y, z minus x. Let us minimize the Lagrangian with respect to x and z so as to obtain the dual function. Since the objective is separable in x and z, we can minimize with respect to each of them separately. So the dual function is given by q of y equal to min over x f of x minus inner product of y, x plus min over z g of z plus inner product of y, z. Let us solve each of these problems separately. First, consider min over x f of x minus inner product of y, x, which can be written as a maximization problem by taking the negative of the objective. So as to write minus max over x inner product of x, y minus f of x. Likewise, we can write the min over z gz plus y, z as a maximization problem as minus max over z inner product of minus y, z minus g of z. Now the first term is nothing but minus f star of y, where f star is the conjugate of f. Similarly, the second term is minus g star of minus y, where g star is the conjugate of g. So finally, we have the dual function, which is given by qy is equal to minus f star of y minus g star of minus y. So here we have the minimum of the primal problem on the left and the maximum of the dual objective on the right. We already know that these two will be equal if strong duality holds. Similarly, we also know that if f and g are proper closed functions, which are convex, and Slater's or strict feasibility condition holds, that is, the intersection of the relative interiors of the domains of f and g is non-empty, then strong duality holds, which is the required statement. The Fenchel duality was first developed separately from Lagrange duality theory. It was later established that both theories are equivalent, in the sense that all the results from one can be obtained from the other. Finally, let us take a look at an example where we can apply these results. The derivation in this example might seem opaque because you will not know why particular steps are being taken. But that's just the way it is. I think the first one who derived it did it by trial and error, and we are simply following in their footsteps. Consider the max function, which we saw earlier, given by f of x equal to max over I xi. That is, we are getting the largest entry of x. Let us calculate the conjugate of the max function, which is f star of y equal to max over x inner product of x, y minus max over I xi. And here, since x is an Rn, the inner product can be explicitly written so that we have sum over I xi yi minus max over I xi. Before we begin, note that this is an unconstrained maximization problem, so there are only two possibilities. Either the result will be finite or it will be infinity. Recall that the domain of f star, which is a convex function, is the set of all y such that f star of y is finite. So we are interested in finding out what are the values of y for which f star of y remains finite. We split into two cases. In the first case, let us examine what happens if any of the yi's are negative. Let's say that yj is strictly less than 0 for some j between 1 and n. Then let us choose xi equal to minus omega for I equal to j and 0 otherwise, where omega is a positive number. So we have set the jth entry of x as a negative number minus omega and all other entries as 0. We can see that f of x, which was max over I xi, is equal to 0 in this case. So in this case, the objective function evaluates to minus omega yj, which is a positive number because yj was negative. Now omega was arbitrary and therefore the objective function can be made arbitrarily large for an arbitrarily large omega. Hence in this case, the objective is unbounded above and therefore any y with negative entries cannot be in the domain of f star. Now to start with, we would not have guessed that we would need to consider this case, but in hindsight you can see that it makes sense. So then let us consider the other case when all the yi's are non-negative. Let us consider for a moment a situation where all the xi's are said to be equal, say equal to omega for some number omega. Then in that case, clearly f of x is equal to omega because all the xi's are equal, and the objective function evaluates to omega times sum of I yi minus 1. Now this immediately tells us as to what will happen if sum of I yi is not equal to 1. You can see that if sum of I yi is greater than 1, I could have chosen omega arbitrarily large, and likewise if sum of I yi is less than 1, we would have chosen omega to be arbitrarily large negative, and in both cases we would have made the objective unbounded above. Now this happens for a specific choice of x, but remember that we are maximizing with respect to x. However, the objective function is already going to infinity for this choice of x, so it does not matter that there is a better choice of x. So in conclusion, we must have the entries of yi sum up to 1 and to be non-negative. This brings us to the final case where sum of I yi is equal to 1 and yi has non-negative entries. In this case, consider the inequality sum over I xi yi is less than equal to max over I xi times sum over I yi, which follows by upper bounding each xi with max of I xi and then taking these terms common. Then let us subtract max of I xi from both sides to obtain sum over I xi yi minus max over I xi less than equal to sum over I yi minus 1 times max over I xi. The right hand side evaluates to 0 because sum over I yi is equal to 1, while the left hand side is exactly the objective function we are considering. So the objective function is upper bounded by 0. We aim to maximize the objective function with respect to x, but under any circumstance the objective function cannot be greater than equal to 0. Therefore the maximum of the objective function, which is f star of y, is either 0 or less than equal to 0. Observe further that the objective function also evaluates to 0 for the choice x equal to 0. In other words, the objective function is upper bounded by 0 and that value is attained for the choice x equal to 0. This implies that f star of y is equal to 0. In summary, the conjugate of the max function is equal to f star of y equal to 0 if sum over I yi is equal to 1 and yi are non-negative, and infinity otherwise, which is basically the indicator function of the set delta n, where delta n is given by set of all y in Rn such that 1 transpose y is equal to 1 and y is non-negative. This is called the unit simplex or the probability simplex. You can see that it is the set of all probability mass functions in Rn. So with this we are done with introducing the Fenchel inequality and Fenchel duality. Before concluding, we take a look at envelope theorem, which is very useful in practice. We will consider its simplified version that is easy to prove, while remarking that a general version also exists. Suppose that phi is some proper closed convex and differentiable function in its arguments, and let f of x equal to min over y phi of x comma y. Let us also denote y of x equal to arg min over y phi of x comma y. Therefore, fx can be written as phi of x comma y of x, because yx is the value that minimizes phi with respect to y. Further, if phi is differentiable, we can write down the optimality condition, which says that grad of y phi of x comma y, which is the gradient of phi with respect to y, evaluated at y is equal to y of x, is equal to 0. So the envelope theorem is a simple result about the derivative of f. Note that f depends on x in its first argument and in its second argument through y. Let us calculate the derivative of f using the chain rule. So the gradient of f with respect to x is given by the gradient of phi with respect to the first argument x at y is equal to y of x plus gradient of phi with respect to its second argument y at y is equal to yx times the gradient of y of x with respect to x. But observe that the second term is 0 from the definition of yx, from the optimality condition of yx that we just wrote. So we have grad of x fx is equal to grad of x phi of xy for y equal to y of x. This is the statement of the envelope theorem. In other words, suppose that we need to calculate the gradient of f at a given point x1, then calculate y of x1 by solving the minimization problem. Next, calculate the gradient of phi with respect to its argument, and finally substitute x1 and y of x1 into the result in order to get the equality. To see the envelope theorem in action, let us assume that f and its conjugate f star are differentiable. This holds under certain conditions that we will see later. Then let us calculate the gradient of f star with respect to y. For this purpose, same as earlier, denote x of y as the value of x that maximizes the objective, so that x of y is equal to argmax over x, inner product x comma y minus f of x. We can see that the gradient of the objective function with respect to y is x. So the gradient of f with respect to y is x of y, which is the argmax of x comma y minus f of x. Note that we stated the envelope theorem for minimization. It is similarly actually applicable to maximization also, as demonstrated in this example. To see why, you can always consider minus f star of y, which would then be a minimization problem, and verify this result. So with this, we are done with our discussion on the two duality theories. In the next video, we will look at regularity conditions for functions, specifically smooth functions.